When solving resistance total in a series circuit, we start by writing the equation. We'll take the resistance value for R1, which you can see is 3 ohms, and we're going to put it up here. Take R2, which we can see is 2 ohms, and we'll put it here. And we add those two together, and we get the resistance total for the series circuit. The next step is we'll take the actual numeric value for R1 and R2 and put them here. So R1 was 3 ohms, R2 is 2 ohms. 3 plus 2 equals the resistance total for the series circuit. And then we rewrite the answer. And the answer is RT is equal to 3 plus 2, which is 5 ohms, and we carry that back and place it with our other values. The next step we're going to discuss is solving amperage total. Previously, we found the resistance total of the circuit, or maybe we already know the resistance total. We'll start by writing the equation, and using Ohm's law to solve amperage, we know that volts divided by resistance equals amps. So we're going to take our total voltage, divide it by the total resistance for the circuit, and we'll get the total amperage for the circuit. So our equation is going to be V divided by R equals amps. So there's Ohm's law. This time, since we want a total, we'll make it voltage total divided by resistance total equals amperage total. I look over at my list and I bring my numbers over. So my voltage total is 12 volts. My resistance total is 5 ohms. So 12 divided by 5 is going to be our amperage total. Amperage total then is 2.4 amps. And I carry that value and place it in my list. We have a rule for amperage total. Amperage remains constant throughout the circuit. This is Kirchhoff's current law. Kirchhoff states current that leaves a node returns to a node. He also says it a little different. The sum of the currents flowing into a node or junction is equal to that which is flowing out. So now that we know the total amperage flowing through the circuit, we know our resistance values of each of the series resistors. We can determine how much voltage is going to drop at each of those loads. So over here on the left we have the voltage drop at R1, we have a voltage drop at R2. To solve the voltage drop at R1, Ohm's law tells us voltage is equal to resistance times amps. So we'll write the equation. We need an amperage, we need a resistance, and we get a voltage. We know the total amperage flowing through the circuit, that's AT, amperage total. And so we'll use AT here times R1 will get us the voltage drop at R1. So we'll bring our values over. Amperage total is 2.4. Look up here on the list, R1 is 3 ohms. So 2.4 times 3 is going to get us voltage drop at R1. So 2.4 times 3, voltage drop at R1 is 7.2 volts. So we started out with 12 and we've dropped 7.2 here. We could subtract the 2 and predict our number here. We're going to go ahead and figure the voltage drop at R2 as well. Rewrite the equation. Amps total times R2 gets us the voltage drop at R2. We'll put the values in. 2.4 times R2. So R2 is right here. Bring that number over. 2.4 times 2 is the voltage drop at R2. Rewrite the answer. Voltage drop at R2 is 4.8. Carry that number over, put it on the list. We have a rule for voltage drops as well. The sum of the voltage drops equals source voltage. This is the second of Kirchhoff's laws. It's the voltage law, or KVL. Also, all of the voltage is dropped across the loads. So what we're saying here is, if we take the voltage drop at R1 and add it to the voltage drop at R2, we should get the source voltage. So here's the one we just did. It's 7.2 volts at R1. We had 4.8 volts at R2. We add those two together and we get 12 volts. Just to back up, 7.2 plus 4.8 is 12.